Hey everyone, I'm going to tell you about how how we can measure distances in astrophysics. This is actually going to take a couple of videos. I'm just going to focus on a tiny part today, and to start off with, I'll tell you about the units of distance that we can use. So we have three main ones: astronomical unit, light years, and parsec. Okay. Now, the astronomical units, or AU, is the mean distance between the Earth and the Sun. So it's the average distance that the Earth is always away from the Sun. The Earth, when it goes around the Sun, it goes around in an ellipse. It's almost like a circle. It's actually an ellipse that is not very complex. I forgot the word, but it's so it's when you can say the eccentricity, there we are. So it's not the eccentricity of the orbit is not very big, okay? It's almost a circle, but still, sometimes we are closer to the Sun than other times. So the astronomical unit, it's the mean distance between the Earth and the Sun, and that's going to be 1.5 times 10 to the power of 8 kilometers, or if I use the units of distance or in terms of meters, how we mostly use it in physics, is 1.5 times 10 to the power of 11, okay? So we use astronomical units quite a lot when you're talking about the solar system. So I can say that a certain planet is 5 astronomical units, and this will give me an idea that is 5 times from us than the distance from the Sun to the Earth, okay? So it's quite useful as well to use this. The other one is light years. Now, light years is really by definition the distance that the light travels in 1 year. So what all you need to do is, you know that velocity equals distance over time, so distance will be the velocity times time. So you multiply the speed of light, which is 2 times 10 to the power of 8 meters per second, times the time in seconds that we have in a year. So 365 times days, times 24 hours in a day, times 60, the minutes in an hour, times 60, the seconds in a, I said the minutes, so I said the minutes and then times 60, which is the seconds in a minute. And if you do this calculation, you get that 1 light year is 9.5 times 10 to the power of 12 kilometers, or if I want to say in meters, is 9.5 times 10 to the power of 15 meters. Distances in between stars within our galaxy, we can say in light years. So again, is instead of saying that a certain star is, I don't know, 20 times 10 to the power of 15 meters, I can say, oh, you know, is in about 2 point something light years away from us. So again, it's quite useful to use them. And then we have parsec. Parsec is by definition the distance where the angle that I would see the object would be of 1 arc second, okay? So it's the distance where the angle will be 1 arc second, and is 1 parsec, which is 3.1 times 10 to the power of 13 kilometers. So in meters, this is going to be 3.1 times 10 to the power of 16 meters. So these are quite useful. So within solar system, we use quite a lot astronomical units. Between stars, light years, larger distances, we use parsecs, okay? There's nothing wrong about using any of them, but it's just what is easier really to use. So I can say that certain galaxies, a couple of parsecs from us. Now I have here this exercise that shows that there are 2.1 times 10 to the power of 5 astronomical units in a parsec, and that they are 3.26 light years in a parsec. This is just for you to have an idea of how much bigger the parsec is in relation to astronomical units or light years. If you want to do this exercise, all that you need to do is divide the parsec by the astronomical unit, and you will get 2.1 times 10 to the power of 5. And then to compare the light year in a parsec, all you do is to divide the parsec by the light years, and you get 3.26, okay? Now, light year is actually a measurement of distance, okay? So we say year, which is time, but is actually, as I told you, is the distance that light travels in 1 year, okay? So light year is a distance that light or any electromagnetic waves travel through vacuum in 1 year. And here it is, that's the speed of any electromagnetic wave. So 3 0.0 times 10 to the power of 8 meters per second. So because the light had to travel to us, it means that when I see something and I say is, for example, 3 light years away, or as in this example, 30 light years away, I am looking at that something, at that object, as it was that many light years ago, that many years ago. So if it's 30, I'm looking at the object as it was 30 years ago, because I had to wait 30 years for the light to reach us. For example, the moon is 1 light second away from us. So it means that it takes 1 second for the light to travel through the moon to us. So that means that when I look at the moon, I actually look at it as it was 1 second ago. All right? So I had here this exercise really quickly. I'll just show you the answers because, you know, if you want to try, pause the video now and then check if the answers match. I was basically saying which type of units would you use for the following measurements. So for the diameter of the moon, we could talk about meters or kilometers. For the distance from the Earth to the moon, meters, kilometers, astronomical units, or light seconds, as you know. It takes 1 second for the light to reach us, okay, from the moon. Distance from the sun to Mars. So we are talking within the solar system, so astronomical units are quite useful. I can use meters or kilometers as well. The diameter of the Milky Way. So I could use light years, which is, so what is the number again? 100,000 light years across, or then if I want, I can say parsec, okay? I also have here some questions for you, which again, if you want, you just pause the video, check if the answers match when I show you in the next video, or if you don't want to do the questions, just, you know, go a couple of seconds forward and you will just go to the actual measurements within the solar system, okay? So I was saying to convert each of the following distances into light seconds, and then I had another one about the average speed of a mission the Apollo mission, and then how long it would take for the spacecraft to reach the nearest star, okay? If you do these exercises, so again, pause the video, and then you can pause the video again, these would be the solutions. So in all of them, you could use the formula that time equals speed, distance over speed. The speed will always be the speed of electromagnetic waves, and these were the results that you would get, okay? So give it a go, try the exercises. If you don't, then let's talk about how we measure distances in the solar system. Sorry, in general, but I'm going to focus on the solar system today. So how do we measure distances? We can have, you know what, maybe I was just thinking, maybe I should do this as a new video. I'll just tell you this and then I'll do the radar in a whole video maybe. Alright, so how do we measure distances in the solar system? Oh my god, why am I talking about the solar system? How do we measure distances in astronomy? So if I'm talking within the solar system, I use radar. So check the other video that I'm going to do next for you to see how it works, okay? For nearby stars, I can use parallax. And for any distances bigger than that, larger than that, then I'll use the apparent brightness. So parallax is about how much the star seems to move according to the background stars in angles. When the star is very far away, then the parallax angles are so tiny I cannot even measure them. So I'll use different methods, which is about apparent brightness. You'll learn about apparent brightness as well already, in the previous video, when I was saying that this is how bright something seems to be from Earth. So we know that the brightness is going to decrease with the distance squared, so I can use the apparent brightness. Examples of things that I can use: Cepheid variables, I'm going to have a video about them. Star luminosities, I'll have a video about them as well. Type 1 supernova, again, I'll have a video, and there are other ways as well that I'm going to talk about in following videos, okay? Whatever we do, we always have some uncertainty, okay? So there are always approximations that we do. So the cosmological distance scale, so all these measurements we take, all these distances that we estimate, they are subject to uncertainty, okay? However, in our defense, and in the defense of every single astrophysicist out there, these are really difficult things to measure. Come on, we are very far away from the objects, so we are still awesome, okay? So I'll make a new video just about the radar, because otherwise I would drag this quite a lot, okay? So I told you about the types of units of distances we can use. Here we go. I even gave you some exercises, and now I'm going to focus on the radar, okay? So see you in the next video, which is going to be about the radar. Bye!